Langchain together chat models summarization. None. This section describes how to effectively utilize multiple large language models (LLMs) together to complete complex tasks. It's essentially about creating a chain of LLMs where each model's output feeds into the next, enabling more intricate operations. Inputs: the raw text or data that the chain of LLMs will work with. It could be a document, a set of instructions, or any relevant information. This refers to the specific LLM models that will be used in the chain, including their names or configurations. Each model might be chosen for its strengths in specific areas, such as text generation, translation, or summarizing. Outputs: the final result produced by the entire chain of LLMs. This could be a refined text, a summary, a translation, or a combination of outputs from different LLMs. This encompasses the individual responses generated by each LLM in the chain. These responses provide insights into how each model processed the input and contributed to the final output. Steps: the first step is to define the overall task you want to achieve and then break it down into smaller, more manageable subtasks. Each subtask will be handled by a specific LLM. The next step is to carefully select the most suitable LLM for each subtask based on its capabilities. For example, one LLM might be excellent at summarizing text, while another excels at generating creative content. Once you have selected the appropriate LLMs for each subtask, you need to chain them together in a logical sequence. This involves defining how the output of one model becomes the input for the next, ensuring smooth data flow through the chain. After setting up the chain, you run it by feeding in the initial input. The models execute their respective subtasks, passing their outputs to subsequent models until the final result is produced. Prerequisites: a basic understanding of LLMs and their capabilities is essential. This includes knowing the strengths and weaknesses of different models, as well as their underlying technology. You'll need to be familiar with popular LLM platforms like Hugging Face, OpenAI, and Google, and their respective application programming interfaces (APIs) for interacting with them. Knowledge of Python and the langchain library is crucial for creating and managing LLM chains. Langchain provides a powerful framework for orchestrating LLM workflows, making the process much more efficient. You can access comprehensive documentation and tutorials on the langchain website to learn more about its features and how to use it effectively. Fine-tune parameters. The weights of an LLM refer to its internal parameters, which determine its behavior and performance. These weights can be fine-tuned by training the model on specific datasets to improve its accuracy and relevance for a particular task. This refers to the configuration of the entire chain of LLMs, including the order of models, the input and output parameters, and any specific instructions for each model. Fine-tuning this configuration can significantly improve the chain's efficiency and accuracy. Challenges and fixes. One common challenge is that different LLMs may have different input formats, making it difficult to pass data smoothly between them. This can be addressed by pre-processing the input data, converting it into a format compatible with all models, or using specialized tools to handle data transformations. Sometimes, LLMs in a chain might produce outputs in different formats, which can cause problems when integrating them. To overcome this, you need to define clear output formats for each model and implement mechanisms to parse and convert outputs into a consistent format for further processing. LLMs often come with different costs and availability. Some models might be more expensive to use than others, or they might not be readily accessible due to licensing restrictions. You can address this by carefully selecting cost-effective models and optimizing the chains configuration to minimize unnecessary computations. Running a chain of LLMs can be time-consuming, especially if it involves complex tasks or large data sets. To improve efficiency, you can optimize the chain structure, minimize redundant computations, and use caching mechanisms to store and reuse intermediate results. Langchain Together Chat Models Chat Together Summary. Chat Together enables collaborative conversations by orchestrating interactions between multiple large language model (LLM) agents. This approach allows for a richer and more nuanced conversational experience, drawing upon the strengths of various agents. Inputs: chat messages from multiple users, allowing for diverse perspectives and input to be incorporated into the conversation. Outputs: a coherent conversation that synthesizes the responses from all participating agents, creating a unified and informative output. Steps: initialize multiple chat agents, selecting the appropriate LLMs for the task at hand. For example, one agent might excel at summarizing factual topics, while another might be adept at creative storytelling. Route messages to appropriate agents based on context and user intent. This ensures each agent is assigned tasks that align with their capabilities. Optimizing the conversation's flow. For instance, if a user asks a technical question, the agent specialized in that area would be chosen to respond. Aggregate and synthesize responses from all agents. This step ensures that the final output presents a coherent and cohesive narrative, integrating the individual contributions of each agent into a unified whole. The goal is to create a seamless conversation experience, even with multiple agents involved. Prerequisites: multiple chat agents, representing different LLMs and their strengths. Examples include popular models like ChatGPT and Bard. Mechanism for agent selection, allowing the system to strategically choose the most appropriate agent for each message. This selection could be based on keywords, user-specified preferences, or a combination of factors. For instance, if a user explicitly states a preference for a particular agent, the system would honor that request. Fine-tune parameters. Agent selection logic, determining how the system chooses the best agent for each message. This logic can be refined based on user feedback and the specific use case. Response aggregation strategy, defining how the responses from multiple agents are combined into a unified output. This strategy could prioritize certain agents' responses based on their expertise or adjust the order of presentation for optimal clarity. Challenges and fixes. Maintaining coherent conversation flow, ensuring a smooth and natural transition between agents. Techniques like prompt engineering and response filtering can be employed to ensure the conversation maintains a cohesive narrative, even when switching between agents. Avoiding redundant or contradictory responses, requiring conflict resolution mechanisms to ensure the conversation remains consistent and reliable. For example, the system could prioritize responses from certain agents based on their expertise or flag contradictory responses for user review. Managing agent workload, ensuring that no single agent becomes overloaded while others remain underutilized. Load balancing techniques can distribute tasks among agents efficiently, preventing bottlenecks and ensuring a smooth conversational experience. This might involve dynamically adjusting the workload based on agent availability and processing capacity. Langchain Together Embeddings Summary. A comprehensive explanation of langchain together embeddings in YAML format. Embeddings are numerical representations of text, enabling machines to understand and process text data. Langchain together is a framework for creating applications that use embeddings to power various functionalities. Inputs. Text data can be in various forms, including documents, articles, or user queries. For instance, you can feed a news article into the framework for analysis or a user's search query for retrieval. Embeddings models are algorithms that convert text into numerical vectors. Popular examples include OpenAI's ADA and Google's sentence transformers. These models are trained on massive text datasets and learn to capture semantic meanings within text. Outputs. Numerical vector representations of the input text are generated by the embeddings model. Each word or phrase is represented as a set of numbers, capturing its meaning and relationship to other words. Similarity scores measure the degree of similarity between different texts based on their embedding vectors. These scores are calculated using mathematical distance formulas, with lower scores indicating greater similarity. For example, two documents with similar topics would have a low similarity score, while documents with completely different topics would have a higher score. Steps. Input text is fed into the chosen embedding model. This could be done through an application programming interface (API) call, by uploading a file, or by directly inputting the text. The embedding model processes the input text and generates a numerical vector representation. This step involves analyzing the words and phrases within the text and converting them into corresponding numerical vectors. The generated embedding vectors are utilized for various downstream tasks. These include similarity search, where the system identifies text similar to a given input. Text clustering groups similar texts together based on their embedding vectors. While machine learning models can leverage these embeddings for tasks like sentiment analysis or topic classification. Prerequisites. An embedding model is essential for converting text into numerical vectors. Popular choices include OpenAI ADA and Google Sentence Transformers, each with different strengths and weaknesses. A method for inputting text data is required. This can be achieved through API calls, file uploads, or direct user input. For example, a web application might use a text area for users to input their queries, while a machine learning pipeline might process data from a file containing text documents. Fine-tune parameters. Embedding model parameters control the behavior of the model during training. These parameters include the model size, which affects the computational cost and accuracy. Training data influences the model's ability to capture specific nuances in the text, while optimization settings fine-tune the learning process. Dimensionality of the embedding vectors refers to the number of dimensions in each vector. A higher dimensionality allows for more nuanced representations but can be computationally expensive. Conversely, a lower dimensionality can be more efficient but might sacrifice accuracy. This parameter involves a trade-off between computational efficiency and the model's ability to capture subtle semantic differences. Challenges and fixes. Dimensionality mismatch between different embedding models can occur when using multiple models with varying vector sizes. This can hinder tasks like comparing texts generated from different models. A common approach is to use a shared embedding space where all models produce vectors with the same dimensionality. Alternatively, adapting models to a common dimensionality can mitigate this challenge. High computational cost of generating embeddings can arise due to the complex calculations involved. This can be addressed by using smaller embedding models, which are less computationally intensive. Optimizing the embedding generation process, such as using specialized hardware or optimizing the model's architecture, can further reduce computational costs. Langchain together embeddings. This YAML describes the together embeddings tool within the langchain framework. This tool's primary function is to generate embeddings for text inputs, enabling semantic understanding and comparison of text data. Embeddings are essentially numerical representations of text, allowing machine learning models to process and understand textual information. Inputs. Text data refers to the textual input that you want to convert into embeddings. This could be a paragraph, a document, or even a collection of text snippets. For example, you might provide a news article to be processed and represented as an embedding. Embeddings model represents the chosen model that will perform the embedding process. Various models are available, each with different capabilities and trade-offs. Popular options include OpenAI's embedding API and Hugging Face models. The choice depends on factors such as accuracy, speed, and the specific application. Outputs. Embeddings are the numerical representations produced by the chosen embedding model. These embeddings capture the semantic meaning of the input text, allowing for tasks like semantic search, clustering similar texts, and measuring textual similarity. The output is typically a vector of numbers, with each number representing a specific feature or dimension of the text. Steps. Load text involves retrieving the text data from the source and preparing it for the embedding process. This might include cleaning, tokenizing, or other pre-processing steps to ensure compatibility with the chosen embedding model. Encode text with embeddings model involves feeding the processed text data into the selected embeddings model. The model then transforms the text into numerical embeddings, capturing the semantic meaning of the input. Prerequisites. Embeddings model refers to the availability of an embedding model that can be used for the transformation process. Several models are readily available through different APIs or libraries. OpenAI embeddings refers to the embeddings API provided by OpenAI, allowing users to generate embeddings for text using a powerful language model. This API is accessed through the OpenAI Application Programming Interface. API and can be integrated into various applications. Hugging Face embeddings represents a wide range of pre-trained embedding models available through the Hugging Face library. This library provides access to a vast collection of models, including those from research papers and community contributions. Users can choose models based on their specific requirements, such as accuracy, computational efficiency, or specialization in particular domains. Text data refers to the availability of the textual input that you want to convert into embeddings. The data can be sourced from various sources, such as files, databases, or web scraping. Fine-tune parameters. Embeddings model parameters refer to the settings and configurations that can be adjusted for the chosen embedding model. These parameters might include model size, layer selection, or specific hyperparameters for fine-tuning the model to achieve optimal performance for a specific task. Challenges and fixes. Incorrect model type refers to the issue of selecting an inappropriate embedding model for the task at hand. Certain models are better suited for specific types of text or applications. If the model is not compatible with the input data or the intended use, the results might be inaccurate or unusable. User-compatible model type involves choosing a model that is suitable for the type of text, the specific task, and the overall application. Researching and comparing different models based on their characteristics and performance can help in selecting the most appropriate one. Memory limitations refer to situations where the embedding process requires more memory than available. This might occur when dealing with large amounts of text or using complex embedding models. Use a smaller model or chunk data involves choosing a model with lower memory requirements or splitting the input text into smaller chunks to process them separately. This can help manage memory usage and ensure successful execution of the embedding process. Langchain together embeddings. This component is responsible for embedding text inputs and outputs. Embeddings are numerical representations of text data, allowing for similarity comparisons and other machine learning tasks. Inputs. This is the text input that needs to be embedded. For example, this could be a sentence, paragraph, or even an entire document. Outputs. The output of this component is a numerical vector, also known as an embedding. Each element in this vector represents a different dimension of the text input. The values in the vector reflect the semantic content of the input text. Steps. The input text is processed by a pre-trained language model, which produces a numerical representation of the text. This process is called embedding. The resulting embedding vector is then returned as the output of the component. Prerequisites. This component requires access to an OpenAI application programming interface, often abbreviated as API key. This key grants the component access to OpenAI's language models, enabling it to perform the embedding process. You can obtain an OpenAI API key from the OpenAI website. The key is typically represented as a unique string of characters, and should be provided as the value for your OpenAI API key variable. This component also requires the langchain library to be installed. The langchain library provides a framework for building and connecting language models, allowing for seamless integration with other tools and components. The langchain library can be installed using the pip package manager by executing the command pip install langchain in your terminal or command prompt. Fine-tune parameters. This refers to the size or complexity of the language model used for embedding. Larger models generally have more parameters and require more computational resources, but they often produce more accurate embeddings. The embedding dimension defines the number of dimensions in the resulting embedding vector. A higher dimension allows for more nuanced representations of text data, but it also increases the computational complexity. The ideal embedding dimension depends on the specific application and the trade-off between accuracy and efficiency. Challenges and fixes. If the embedding dimension is too low, it may not capture enough of the semantic meaning of the text, resulting in inaccurate similarity comparisons. To address this issue, increase the embedding dimension. If the language model used for embedding is not powerful enough, it may struggle to capture the nuances of the text, leading to less accurate embeddings. To improve the quality of the embeddings, consider using a larger and more powerful language model. Langchain together chat models. Chat together. Chat together is a tool within the langchain framework that allows users to interact with multiple conversational AI models, like ChatGPT and Bard, simultaneously, creating a unified conversational experience. This tool effectively combines responses from different models, offering a more comprehensive and nuanced response. Inputs. User input refers to the text or query submitted by the user to the Chat Together tool. It could be a question, a statement, or a command. Chat models represents the various conversational AI models integrated within the Chat Together tool. These models can be different in their strengths, capabilities, and underlying technology. For example, ChatGPT and Bard are two popular chat models that are known for their ability to generate human-like text and engage in conversations. Outputs. Combined response is the final output generated by chat together, which is a consolidated response from all the participating chat models. It aims to provide a richer and more balanced answer to the user's query by integrating insights from different models. Steps. Receive user input involves capturing the user's query or input and making it available to the chat together system. This step ensures that the system is ready to process and respond to the user's request. Route to appropriate chat model involves selecting the most relevant chat model based on the user's input and the model's capabilities. For instance, if the user asks a question about a specific topic, the system might choose a model that specializes in that domain. Receive response involves retrieving the response from the chosen chat model. This step ensures that the system has collected the necessary information from the AI model to proceed with the response generation process. Combined responses involves consolidating the responses from all the participating chat models into a single, coherent response. This step aims to integrate diverse perspectives and insights from different AI models to provide a more comprehensive answer to the user's query. Prerequisites. Chat models refers to the conversational AI models that are necessary to operate the chat together tool. These models are the core components that provide the conversational capabilities of the system. ChatGPT is a popular large language model developed by OpenAI, known for its ability to generate human-like text and engage in conversations. It can be used for various tasks such as writing stories, translating languages, and answering questions. Bard is another powerful conversational AI model developed by Google. It is known for its ability to access and process information from the real world, providing factual and up-to-date responses. Langchain is a framework that provides tools and libraries for building and deploying applications that involve interacting with large language models. Langchain simplifies the process of integrating AI models into various applications and provides functionalities for managing the interaction between models and users. Langchain 0.0.250 indicates the minimum version of Langchain required to use the Chat Together tool. This specific version provides the necessary functionalities and compatibility for the tool to operate effectively. Fine-tune parameters. Chat model weights refer to the relative importance assigned to different chat models in the response combination process. By adjusting the weights, users can prioritize responses from specific models based on their perceived accuracy or relevance. Response combination strategy refers to the method used to consolidate the responses from multiple chat models into a single, cohesive output. Different strategies can be used depending on the specific requirements and the nature of the responses from different models. For example, a simple approach could be to concatenate the responses, while a more sophisticated approach could involve summarizing or extracting key insights from the responses. Challenges and fixes. Handling conflicting responses refers to the challenge of managing situations where different chat models provide contrasting or contradictory responses to the same query. Use a weighted average or majority vote refers to a strategy for resolving conflicting responses by assigning different weights to different models and selecting the response that receives the highest weight or the majority vote. This approach aims to minimize the impact of any single model's biases or inaccuracies. Maintaining conversation context refers to the challenge of preserving the continuity and coherence of the conversation as it progresses. Use a memory component to store previous responses refers to a strategy for preserving conversation context by storing the history of the conversation. This allows the system to access and reference previous interactions, ensuring that the responses are consistent and relevant to the ongoing dialogue. Use a separate model for context management refers to a strategy for managing conversation context. By using a dedicated model responsible for maintaining the history and context of the conversation, this allows the primary chat models to focus on generating responses, while the context management model ensures that the conversation stays coherent and relevant.